very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. And today we'll be talking about distribution network reliability. And reliability is one of the important component of any network and specific to distribution system. Now, in the module 5, we'll be talking about reliability analysis. Then we'll move to probabilistic failure analysis of network components, reliability matrices, value of loss load calculations, system reliability enhancement technologies. Now, let us start with a very basic introduction to reliability analysis. Now, there are two different things. One is reliability and adequacy. So, reliability and adequacy defines two separate but interdependent concepts. The term reliability describes the security of the system and the avoidance of the power outages, whereas the term adequacy refers to having sufficient system capacity to supply the electric energy requirements of the customers. Now, if you see reliability, availability and power quality, they are quite interconnected. First of all, to start with, availability means sort of interruption duration, up to what extent the energy is available to me. Then moving to reliability, which is sustained interruption frequency and momentary interruption frequency, and power quality basically looks into different kind of issues such as noise, sag, swell, flicker, transient, frequency variation, harmonic distribution, everything looks into the power quality aspects. So, a quality power means which is not only reliable, but also possess the best quality of electricity that is available to me. Now, reliability mainly divided into two important subgroups. One is adequacy and the other one is security. Although there are adequate methods for evaluating distribution system reliability, there are insufficient data on reliability performance to identify the most cost-effective distribution investment. Most distribution interruptions are initiated by severe weather-related interruptions, with a major contributor being inadequate maintenance. Now, distribution system reliability can be improved by the timely identification and response to failures. Now, look at any distribution system. Now, most of the time, if you do not have access to electricity, that does not mean that we do experience a peak energy deficit or shortage of energy, but maybe energy is available to me, but the system, the low voltage network is not reliable to cater electricity to the residential colonies. Now, classification of generic specific causes of outages. Now, first is weather specific, and the weather specific could be due to snow, cold, flood, heat, hurricane, ice, lightning, rain, tornado, wind, and many others. Now, when you talk about system components, they are as good as you can see electrical and mechanical failures. We can also experience insulation failure. We can also experience voltage control equipment failure, and finally protection and control failures. Now, fuel supply, generating unit failure, transformer failure, switchgear failure, conductor failure, tower pole attachment failure, they fall under electric and mechanical failures. Now, transmission line, substation, surge arrestor, cable failures, they fall under insulation failures. Voltage regulator, tap changers, capacitors, reactor, they fall under voltage control equipment category. Similarly, under protection category, we can experience relay failure, communication signal error, and supervisory control error. Now, there are different components in any distribution system, and due to many weather reasons, those components actually may fail. Now, when you talk about classification of generic and specific cause of outages, we can have some other variety of causes, not necessarily weather failure. They are airplane or helicopters, maybe due to animal, maybe due to vehicle, maybe due to digging exercise, maybe due to fire, sabotage, tree, and there are many other aspects that is not known to anybody. And system operation could be, like system conditions, public appeal, voltage reduction, and utility personnel. For example, sometime the system may experience stability issues, high and low voltage issues, high and low frequency issues, line overload, unbalanced load, neighboring power system, and so on and so forth. Now, public appeal, which is either commercial and industrial or all customers. Now, in case of voltage reduction, it could be varying between 0 to 2% of reduction, or sometime 2 to 8% voltage reduction, or sometime rotating blackout. Now, in case of utility, we can have system operator error, we can experience power plant operator error, field operator error, and finally the maintenance error. Now, when you talk about classifications of different kind of reliability issues, now type of events, generic subsystems, and generic causes are three different categories under which the percentage of probabilities for which we can experience the outages or reliability issues. For example, when you focus on types of events, we experience actually customer outages close to 50%, and reduction is close to 40%, and hazards may be close to 10%. Now, in case of generation failure could be, or generation issues related to 55%, and transmission which is around 38%, and distribution is 7%. Means if there is a system reliability issue, maximum percentage of reliability issues falls under generators, and then transmission and further distribution. Now, electric system operation level, it is 46%, electric system component level, it is 29%, weather it is 15%, and miscellaneous it is close to 10%. Now, defining appropriate reliability, it is neither feasible nor economical to avoid all severe interruptions, because it is almost impossible to make sure that the system will never fail. Appropriate reliability occurs when the cost of avoiding additional interruption is higher than the cost of interruptions themselves. Optimal reliability is reached when the sum of the supply cost and interruption cost is minimized. Investment in reliability does not yield linear improvement. Diminishing returns do apply. Now, when you talk about cost effectiveness considerations, focus should not just be on absolute reliability level, but on the incremental benefit per dollar or rupees invested. There are a couple of key questions that comes to mind. Where should the next rupees or dollar go to achieve maximum reliability gain? Means, what is that area where I have to invest my next penny? Now, in case of utility operational options, aside from reconfiguration and sectionalizing, the main operational method to enhance reliability is to timely repair of failed equipment to minimize outage duration. Now you can see that there is an optimal reliability level where investment yields maximum cost effectiveness by minimizing customer damage cost from supply interruptions. So as reliability improves, maintenance cost decreases, customer damage cost also decreases, customer satisfaction rises with improved reliability. So you can see the relationship between reliability and economics from the figure 27.2, which clearly highlights how the customer's economy and reliability are completely interconnected and closely associated. Now, the right hand side figure 27.3, that is cost versus system reliability. The figure illustrates the relationship between investment in system reliability, resulting level of reliability, and total cost, that is supply cost plus cost of interruptions. Now, if you see this diagram, you can see the total cost, and this is my optimal cost, investment cost, cost of interruptions, and optimal reliability levels. Now, when you focus on key insights, as reliability increases, total cost initially decreases, reaches a minimum, and then increases due to higher investment. The optimal or appropriate reliability level corresponds to the point of minimum total cost, and this confirms the idea that beyond a certain point, improving reliability is not at all economically justified. So, it is very important to identify what is that optimal point for my investment. Now, renewable energy sources, considering today's important component of generation, they do also being part of, due to their intermittency, a lot of challenges, stochastic nature, I think the reliability also sort of serious concern when you have system integrated with renewable energy sources. Now, renewable energy sources such as wind and solar affect power system reliability in both positive and challenging ways. Good that it is bringing a lot of green energy to the system, but nevertheless, because of its uncertainty, we cannot rely on a renewable energy sources completely, primarily due to their variable, intermittency, and stochastic nature. Now, the positive effect on reliability, that means it is improved supply redundancy, adding distribution or adding distributed renewable energy sources increases the number of generation point, which can reduce the frequency and duration of outages at distribution load points. Means if you add renewable energy at different low voltage networks, so that will help you to be free from frequent outages. Now, renewable energy also support for load during grid disturbances, that is when integrated with energy storage or hybrid system, renewables can continue supplying loads during faults or peak periods, thereby improving availability indices such as SAIDI and SAIFI, that is SADI and SAFI. Distributed renewables reduce dependency on long distance transmission, improving local reliability, that is decentralization effect. Now, there are a couple of negative challenges or negative effect on reliability due to renewable energy sources. The first one is very common, that is intermittency and unpredictability. That means either it is wind and solar, wind or solar, outputs are weather dependent and non-dispatchable, leading to supply demand mismatch if not well forecasted and backed up. Now, increased complexity in system operation, that is managing variability and ramping requirements, imposes stress on system operators, increasing operational uncertainty, reduced inertia and frequency responses, that is high penetration of inverter based renewables can lower system inertia, affecting dynamic reliability during disturbances. As you will know that when my rotating mass is keep on reducing due to PV, then the system inertia is also keep on reducing. Now, risks of energy not supplied, that is ENS, in poorly planned systems, over reliance on renewable without adequate backup, such as storage, can increase outage risk. That means if you do not have any backup due to any emergency, it may so happen that the system may not be able to get any electricity or energy supply due to renewable because it is completely unpredictable due to its intermittency nature. Now, one more important part when today we are talking about the modern distribution system in which information and communication technology, that is ICT, is part of it. Now, if you have ICT enabled distribution systems, what are the positive impacts? I mean, does it enhance the reliability of the system? Now, if I talk about area, which is contribution of ICT, let us see what are the areas where ICT can play a critical role and how ICT can contribute to the reliability of a system. Now, first of all, if I talk about monitoring and control mechanism, in which real-time monitoring via PMUs, SCADA and BAMs enhances situational awareness. Similarly, in case of autonomous and self-healing, faster detection and isolation of faults with intelligent relays and automation systems, demand response and DER integration, better control of loads and distributed energy resources, improving system adequacy and resilience, reduced outage duration, that is ICT reduces frequency and duration of outages, improving SAIDI and SAIFI indices. That means SAIDI and SAIFI, there are two indices, can certainly be improved. Now, in case of flexibility and scalability, which enables dynamic reconfiguration, load forecasting and DER coordination. Now, there are a bit of negative impacts. For example, cyber attacks and cyber power independencies is not possible due to a core ICT integration with the network. Now, first of all, let us understand what is the negative impact on system due to cyber power interdependencies. Direct interdependencies, failure in ICT can cause direct failure in power components, EMU failure, circuit breaker failure, and so on and so forth. Now, in case of indirect interdependencies, ICT failure may not immediately impact power system, but make them vulnerable to future outages. Now, concentrating on cyber attacks, denial of services, false data injection, and malware can happen due to ICT integration, due to which tamper with monitoring such as SCADA energy management system is possible, which may trigger wrong control actions and cause blackouts or misoperations or maloperations. So, you could see that ICT is certainly an important component of any distribution, modern distribution systems, but you do possess some reliability challenges. Now, if the ICT infrastructure fails, let us assume, then functional failures such as device cannot send or receive signals, network failures, latency, packet loss or corrupted data leads to loss of visibility or control, reducing reliability. Now, how does it impact environmental and weather? Adverse weather, that is storms or cold cover, affect wireless ICT networks, weakness the effectiveness of communication, especially in active distribution network, popularly known as ADNS. Now, maintenance is an important component of the reliability study because many times what we realize, the system failure leads to unreliability, and if you continuously maintain a system, certainly its reliability can be extended. Maintenance is central not only to reliability but also to adequacy in power system because it directly affects the health, availability and performance of system components. Now, why do we believe that maintenance is central to reliability? Maintenance play a key role in this by reducing failure rates, by improving component availability, also by enabling conditions based interventions and enhancing system security. Now, the maintenance is central to adequacy because maintenance supports adequacy by ensuring generation capacity availability, maintaining load serving equipments, avoiding energy not supplied, and supporting demand response and DER integrations. So, what we want to conclude here that the maintenance is not only part of reliability, but adequacy is also depends on your maintenance strategies. Now, there are different maintenance approaches. We can carry out different analysis and different strategy or algorithms. We have different methods for maintenance. Some of them are stochastic based, some of them are linear programming based, some of them are meta heuristic technique based, some of them are control theory based, real time data based, and ML or machine learning based. Each one of them do have certain strength and limitations. So, I think you can see from the table where clearly it has been mentioned the strength and weaknesses of different strategy algorithms for your maintenance. With this note, we are coming to an end of today's lecture. Thank you very much for your kind attention. Bye bye.